All right, DBF team, we've reached the end of the line for statics. If you guys haven't kind of figured it out by now, we've basically been talking through some of the key concepts that you learn in AA 210 statics, or your engineering statics class, and trying to apply it a little bit more to the actual aircraft. Now, that's not entirely possible for all the concepts because some of them are just fundamentals that you need to know in order to make further analyses. But for the most part, especially with that shear diagram we covered last videos, you guys were able to see why we care about knowing what that curve looks like. It allows us to figure out where the maximum shear is. It allows us to know how strong a material needs to be in certain areas, etc., etc. Now, after these two videos on moment diagrams, which is what we're covering today, we'll start talking about stresses and strains and displacements and beam bending and a lot of that more applicable concepts, I'll say. But a lot of that, it draws from the very fundamentals that we've covered over the last couple of videos. You'll see that especially because, for example, let's consider stresses. Stresses depend on force over area. Now, area can be easily figured out, but force has to be derived from the definitions of distributed loads, from the definition of what a shear force is at a certain point. All of these concepts will add into what stress is, will add into what then therefore strain is, and will characterize how we view displacement. Boundary conditions are going to be huge. All of these different concepts all come into play later on, which is why we're spending so much time covering them now. So today, in the same way as we covered the shear diagram last time, we're going to be covering the moment diagram with the same examples. This way you guys will have a good understanding of what it looks like to take something from a shear diagram and translate it into a moment diagram. It's going to be very helpful. I hope it's going to be very helpful. One of the key things you're going to realize is you need both the shear and the moment as a function of x in order to do a lot of higher level analysis. That's going to be the building block of what you're going to do when you're calculating stresses, when you're calculating displacements, when you're calculating bending. All of these different things are going to all rely upon what you get out of these diagrams. So they're very important. And I didn't realize that as a student. I realize it now. And for me also, kind of talking to you guys through all this stuff, it's been a really good refresher and allowed me to really solidify some of these concepts. I wish I did it sooner. So this should be applicable for all of you, regardless of whether or not you've taken statics or going to take statics, or maybe you're a junior like me. It's always good review to understand how you derive this diagram. So without further ado, let's go ahead and get started. I'm just going to throw up the diagram for that rectangular load. I'm going to throw up the shear equation, and I'm going to throw up some of the boundary conditions. And we'll go and derive moment based off of that. Alrighty, so hopefully these look familiar. Reaction at y in the positive y direction. I always do this. I'll draw the coordinate system. There we go. So positive W naught L is Ry. Counterclockwise we define as positive for moments typically, and that's expressed as W naught L squared over 2. If you're wondering where that came from, remember we applied the rule of centroids. We took the force, we turned it into, or we took the distributed load, turned it into an applied force at a point, and that point falls at the centroid of the load. For a rectangle, the centroid is exactly in the middle, so W naught L is the entire force. That's applied at a distance of L over 2 from our reference point, which is the boundary, or the boundary condition at the wall, which is why we get W naught L squared over 2. Again, useful concepts. Remember how centroids work. Very important. And in last video, we derived that V of x is equal to W naught L minus W naught x. And that doesn't matter if you're going right to left, left to right. It doesn't matter. It's the same equation. All of these equations are the same no matter which way you derive them from. So it's actually a really good sanity check to do multiple derivations and to see if your equations match. Because if they don't, you've probably made a mistake. Or not probably, you've definitely made a mistake. Okay, So let's go ahead and calculate what our moment equation is. Now, for shear is a force. Shear is a force. So we solve that using a force balance. Again, this is shear in the y direction. So we are able to solve that simply by taking a force balance in the y. F of y equals to 0. And then we sum all of the forces in our body. Remember, we made that infinitesimal cut. We cut it into two pieces, and we picked either the left or the right side, and we did all of our calculations on one of those sides. It's going to be basically the same for moment. You do the same thing, except instead of summing forces, you're summing moments and setting them equal to 0. So fundamentally, the way we solve this is by the sum of moments about a point, we'll just call that point 0, is equal to 0. So it's the same thing we did before. The trick is, where do we take all of these forces to be applied as moments? So let's go ahead and let's draw, let's do it left to right to start. Let's just do it left to right. Let's draw what that looks like. I know it's a little bit messy, but hopefully this makes some sense, right? We make a cut which exposes the internal shear force, it exposes the internal resistant moment, and we have our coordinate system defined. We're going from x is equal to 0 all the way out to x is equal to L, so we don't have to change anything there. So we simply have x. Our distributed force is W naught times x, and our Ry is solved here, and our moment resisted at the wall is solved. So all we're going to do here is do a sum of moments. Now, what we have to consider first is, where should we apply all of these forces? What distances should we use? That's going to be very important. So what we're going to do here is, let's identify what the forces are and moments that are acting on our body for the moment balance. So typically when I do it left to right, I take the moment about the wall, right here, about this point. This is a stationary point. It's not going to move. As I move in x, this point will always be x is equal to 0. So I'm going to say the sum of moments about here. Let's just call this point O, point 0. It's 0 on the x. What do I have? Does Ry contribute a moment? And the answer is no, because a moment is a force times a distance. And remember, it's not just a force times any distance. It's the force times the perpendicular distance. Right? So if I've got a force acting upwards over a distance to my point here, that's going to create a moment like this, right? If the force is acting this way, or let's do it with the pen. The force is acting in this direction, but the force arrow is like here or something, and my point's here. There is no perpendicular distance. This force is basically acting through that point. It's just been drawn over here. There's no moment. Very important to remember that. So Ry has no perpendicular distance to point O. So it does not contribute to a moment. What does contribute to a moment, however, is our distributed body load. W naught contributes to a moment. W naught times x applied at the centroidal distance x over 2, right? X divided by 2 is right in half. That's going to contribute to a moment that's going to be clockwise. V of x is going to contribute to a moment that's going to be clockwise at a distance of x, because that's exposed at whatever the cut is. Moment exposed, I've drawn it because I like both of my arrows to kind of be in the same area. So if my V of x goes down, my moment arrow will hit it as well. I just do it like that. Your moment is also going clockwise, right? All of these are negative, and in the way we've drawn it, have to be opposed by our counterclockwise moment. So we simply write the balance as follows. Moment is positive. This is our body force, okay? That's right here. Keep saying body force. This is our distributed load, right here, right? W naught x times x over 2, because that's going to be the distance to the centroid of the load. We're doing moments. We're not doing shears, so you need to bring in that additional term. That's why that's squared, and that's to the power of 1. Power of 1, power of 2. Every time you go to a moment, you typically step up in the power, because you have to multiply by that distance. I don't know if I told you guys before, but the units of moments are typically Newton times meters, not just Newton, which should make sense to you because you're multiplying by a distance. Okay, so m minus w naught x squared. Now we have v of x, and again, it's going to be clockwise, so it stays negative, minus v of x times distance x, right? Because this distance, x, is the point at which v of x will act, minus m of x. And now what we've done is we've accounted for every single force that can create a moment about point O. And by summing it equal to 0, we can figure out what mx needs to be in order to properly balance these moments and make sure that they all go to 0 at any point, because that's how we satisfy equilibrium. Remember, by doing this, what we're doing is exposing an internal force and an internal moment. And that's what the material is resisting at that point. That's the whole reason why we do these diagrams. So now, I'm not going to make you guys do the math, or I would ask you guys to do the math. I'm not going to do all the math because I've already done it. It's quite simple. All we're going to do now is move mx to this side, and then plug in all the values we've already solved for, and be very methodical about solving the equation out, watching our negative signs. It's all basic algebra. You can do that. You guys are very capable of doing algebra. Okay? And I would encourage you guys to do this algebra because you can check my work. I am 99.9% confident that I've done it correctly. But if I've done it wrong, leave a comment. Bonus point goes to you if you found a mistake. But it's just algebra. V of x gets plugged in as w naught L minus w naught x right here, multiplied by x. Moment gets plugged in as w naught L squared over 2. And we basically solve for m of x, which I'll do here shortly. So after you do a little bit of tedious algebra, it's not that bad, you're going to end up with an expression that looks like this. And what this is here is it's an expression of the moment as a function of x as you move along the beam. But how do we know it's the proper expression? Well, we have to perform our sanity check. What is that? Let's apply boundary conditions to this equation and make sure that it satisfies those conditions for x is equal to 0 and x is equal to L, because that's where we truly know what the behavior should be. So if we plug in x is equal to 0 here, what should we get? Well, we have to get m, because as soon as we get to this point where x is equal to 0, we've not accounted for any body force or shear force and all that. It disappears, and we're taking it about 0.0, which is only going to be m. M is a reaction moment. It has to equal m when x is equal to 0. Does it? Well, this term will drop to 0. This term drops to 0. We're left with w naught L squared over 2. But now you're saying, hey Ethan, there's a negative sign. Why is there a negative sign? Negative w naught L squared over 2 is not the same as w naught L squared over 2. And you'd be absolutely correct. It's not the same. But why is it negative? Because if you look here, we've defined moment as being counterclockwise, or we've defined moment as being clockwise at the cut. As we move this all the way to this point, x is equal to 0, you can see that the reaction moment is in the opposite direction. So what that's telling you is, at x is equal to 0, your m of x is negative w naught L squared over 2, which means the direction goes the other way. And when the direction goes the other way, that allows it to match exactly what is m. So that negative sign is very, very intentional, and it shows you that you may have drawn the moment in this way, but at this point, it goes the opposite way. So that's super crucial. Watch your negative signs. They do matter. Oh yeah, second boundary condition. X is equal to L. It needs to go to 0. We cannot have a moment resisted on this very, very rightmost end of the beam because it's touching air. There's no more beam left to resist anything. So we can plug in L here. And if you plug in L to this equation, I'm going to have w naught L squared over 2, negative w naught L squared over 2. These combine to make w naught L squared. and this term is positive W naught L squared, it all cancels, it goes to 0, as expected. So therefore, that's why I'm very confident in my equation, because to come up with an equation that satisfies the boundary conditions that is still wrong, it's quite hard to do. So I'm confident in this, but I encourage you guys to go through the algebra, it's not that bad, and actually calculate what this is for you. That's going to allow you guys to actually go through the experience of solving this. But now you're like, okay, this is rather long and drawn out, and it is. This is a conceptual approach to the problem. But if you look at the diagram, and this is a very interesting relation, when you look at the shear diagram, all we're doing with the moment is we're stepping it up a power. And what actually ends up happening, I'm not going to dive into the details of why this is so, but actually, moment is the integral of shear. Interesting. Indeed it is. This is conceptual. Now, the other way I'm going to show you how to solve this. Now, remember, you could also go right to left. You just have to change your coordinate system to be L minus X, etc. We'll tackle the triangle problem like that. But you can also solve this by integration. Integration with boundary conditions, and you're going to get the same result. So we're going to leave this up here on the board. I'm going to erase some stuff over the top, and let's just do a quick integral. And I want to prove to you guys that by taking the integral of shear, indeed you will get moment. All right, so let's set up our integral. So simply taking the integral of shear, okay, so the integral of W naught L minus W naught X, that's going to give us, we're taking the indefinite integral, so there's going to be a constant, W naught L X minus W naught X squared over 2 plus C equals to M X. You simply have to solve for C. What is C? Okay, so now we impose our boundary condition. Okay, so at W naught, so now we impose our boundary condition. At x is equal to 0, we have to solve for C. C is, of course, going to be negative W naught L squared over 2. And you're like, wait a second, why negative? Same reason. We've drawn, well, I erased it, but before we had drawn our moment acting in a certain direction. We have to flip that direction to have it go counterclockwise at M. And this is where the confusion happens. Because if you simply integrate it and you're a bit uncertain about how you should draw your moment and your shear and all of that stuff, you might not know the sign on this term, which might make it pretty hard to be very confident in an equation. Another way to do this, if you're a little bit unsure about the sign on this term, is, okay, x is equal to L. When x is equal to L, what should I get? And if you do x is equal to L and you have to make this go to 0, you will indeed know that W naught L squared over 2 is your answer, because that's the only way you cancel out this term. That's another way to check. But at the same time, for me, by doing these integrations, I always am left with a little bit of uncertainty as to whether or not I properly identified the directions of my shear and moment. There's always a little bit of an uncertainty. Really, it's a good method because, again, by imposing boundary conditions, you know exactly what this term should be. It has to satisfy both of those conditions. But I prefer this method because I know exactly what's being accounted for. But this is a lot more work. It's more algebra. So once you get confident enough that you're identifying your boundary conditions properly, once you get confident enough that you know how to identify what your shear and your moment directions are at the cut, quick tip, I would just stick with this convention where it's always down and always this way. So moment is that way, shear is that way. That works for me. Your professors might tell you something different. I don't know if convention is different, etc., etc. This is what I like. But there you go. That's how you derive the equation. So now we can go ahead and draw the diagram. And this is why you do your directions the way you do. Because now remember, we're at negative W naught L squared over 2 at the wall. Remember how shear we drew positive on the bottom? Well, by doing this, when you have a positive shear, the way I've defined my coordinate system, they're both going to be on the same side, moment and shear. And we know it has to be this here. We know that at x is equal to L, we have to be at 0 at that point. And now it's quadratic. And if we really want to know the shape of the curve, we can solve for that extra point. So let's do L over 2. When it's L over 2, negative W naught. Now I'm believing it should be that. That's going to be about there. So now we can draw our curve. And this should make sense to you. We had a linear shear function. Therefore, we have a quadratic moment function. And you're going to see if we have a quadratic shear function, we have a cubic moment function for the triangular case. But there you go. That's a moment diagram derived analytically and just by the integral. The integral is a lot faster, but again, if you really want to understand the concept, I highly encourage you to do it with the centroid method. I like that better. Anyway, okay. So next video, we're going to tackle a little bit of a harder case, triangular distribution. And then I'll talk a little bit more about application. And that will conclude basically the summary of what you would probably take away from AA 210 statics. Remember, these videos are tasked as a good review for those of you who have taken the courses. But for those of you who haven't, it gets you guys thinking about how we actually apply these concepts. So when you do take the course, it all clicks. It all makes a lot more sense. So hopefully this video was informative, and I will see you guys next video.